Good morning. Today I'm going to talk about what happens once we have our metrics. And now we're talking about uncertainty, statistics, and some reproducibility. And for that, there is again a bunch of things to load that comes with every notebook, lecture notebook. So I'm not going to say so much about these, just the usual ones. Then there is a lot of books. The two top ones we have seen before. Then there are some about statistics and uncertainties. They are reference material. I don't expect you to read them all, but it's good go-to positions if you want to look into these things. And then again, a lot of papers and sites, some videos and podcasts, some fun, some serious. That one is quite fun. That one, if you played Minecraft once, that's also quite a fun one, because apparently if you sit in a boat and fall a long distance, you don't die. If you jump without the boat, you die. That's what that is about. Kind of fun story. And some slides too. So what we have done until now is quite a lot. We are now actually in lecture 8, and we have looked at data, we have looked at how to enhance the images, looking at different contrasts, minimizing the noise, understanding histograms and how to use them for the segmentation. Once it's segmented, labeling the different components and doing shape analysis on them, even looking into more complicated shapes. So we have a lot in the backpack now to work with, and now we actually have reduced the data to smaller pieces. So from having the huge images, we now have rather tables to work with. And this brings us now to discussing what is actually the meaning of doing our images and seeing how well can we trust our data, and also how can we make conclusions from this data. And the last parts here about parameterization and visualization, I'm not sure if I managed to bring that in today, because I added a new section compared to last year. So, quantitative big imaging is the name of this class. And until now, we have been talking about imaging, image processing, but first of all, what does big mean and what does big imaging mean? So big is, depending actually who you ask. For you, big may be what doesn't fit into your laptop. If you talk to the people at the computing centers, they say big is what doesn't fit in the hard drives of a computer rack. That's big. Some other people, like Google, they say, okay, a whole server center is big. So it depends a little bit on who you ask what big is. But in principle, what it is you need a lot of volume of data. You need also to introduce the velocity, that things need to be handled in reasonable time. And also you need variety. And for that, you need to be flexible. So your code that you use for analyzing the data should be scalable and ideally fast, because you don't want to wait 2 years to get your result, because then your project is probably over already. And it should also be rather easy to customize. So, and for imaging, that is actually also the same thing. It actually starts in the data production, what kind of imaging machinery you have, and also the type of experiments you do. And you actually fill in all these. So if you do a time series of tomographies, then of course you get large data volumes. And in some cases, you also get them in very short time. And then you need to be able to handle that. And also, of course, if you have a couple of terabytes from your experiment, then you need also a strategy how to work with it in a reasonable way. So let's say we want to make some experiments, and we want to get some metrics out. So that is actually what we talked about in earlier lectures. And then we have to make sure that it actually makes sense. And that is what we're talking about today with statistics and uncertainties. So what you want to do is more often that you have some treatment you want to investigate or some process you want to investigate. But in order to know if it's right, you need also to do a control. And then you want to compare the control versus the treatment in some sense. And what you also want to do is to see, that's actually an evaluation of your processing. How well does your processing actually act? If you tune different parameters, is your workflow insensitive to change of resolution, filter parameters, segmentation approaches? So there we need to evaluate which parameters are actually the best and how robust it is around these parameters. And then we come to the validation. We actually already talked about that before in both the filtering and the segmentation, where we worked against ground truth to validate that we actually do the right thing. And then is the question finally, that is actually the part which I'm not sure I'm going to talk about today, but anyway, often when you present your data, you want to visualize it somehow, and then is the question how and what rules actually apply when you want to show your data. So let's come back to our cell image that we have looked at a couple of times already. So we have been able to do a lot of things in this image, getting rid of the noise, finding the cells. We can also analyze the different shapes of these cells. You can see if they are joined somehow or separated, and then the separation was using the watershed that I presented last week. And then we need some metrics to characterize. We looked at the region properties, volumes, etc., and parameters and anisotropy, a lot of parameters that we talked about. And then we get some regions and we get a lot of metrics. And now is the question how we can actually do something meaningful with it. So this is the starting point. And now I'm actually taking back a couple of steps in a general concept where we talk about the scientific questions. If you want to look at correlation or causation in your experiment. So if you look at the correlation, you look for a statistical connection between different data sets. So it's easy to show actually, because you have the equations for it. It's quite quick. But causation is more difficult, because then you want to see if introducing a certain effect actually does something to the observation afterwards. And it can be difficult to show and sometimes even impossible to prove that it actually is there. But experimentally, under right conditions, you can show it. We have different types of experiments that we can do. We can do an observational experiment. So for example, you just suck out a lot of statistics from some database, and then you have some idea what you want to observe from that data. Or you can do a controlled experiment where you more control the parameters. So we can look at large data sets, looking for trends. The population hopefully is random, but not for sure. It's not always a hypothesis-driven investigation, but And it's hard to really see a causation in this data because it's just random what you get. So for example, we can do an observation. We examine 100 people and see that the ones with blue eyes are 10 centimeters taller, including me. That is just an observation that we can see from the data we have. Or we have baked 100, there was 100 cakes baked, and we see a 0.9 correlation between the baking time and the bubble size. Yeah, it's just observation, but you haven't done anything more than just baking cakes without any control. And if you do the control experiment, is actually what we mostly do. We actually specify different sample batches, and we control what they do or how they were created, and with that we can make observations. And that can actually lead to causation, because if you introduce a factor, like examples here, we have 50 mice, and where we have some gene switched off, and 50 mice where the gene is on, and we can see that there is an increase in the population of one population of 10% in the foot size. We can also say that if we increase the temperature of our batch, then the number of pores in the cast metal increased by 10%. It's also, we have done something in order to get an effect. Then we have also our assessments, actually that is from lecture 1, where we can do a qualitative investigation or a quantitative. Qualitative, you can observe things, but you cannot really put a number on it, or else you can look into really quantifying different regions and telling what they belong to, and that is then the quantitative. And the qualitative assessment, even though it doesn't give you numbers, can be very useful. Usually you do it in the initial part of your experiment, where you want to get a quick visual feedback, because human eye and brain are quick to see patterns, and you can see what makes sense, at least if it's obvious. There are cases where it's less obvious, then it's not so easy to do the qualitative assessment, but you can see and compare to expectations from previous techniques. You can also see if you have artifacts in the data. That's a quick one, actually. Or if the shapes look correct. If you expect cubes and get spheres, then yeah, of course, you have to think about what you have done to the data or what you measured. Maybe there's a reason beyond what you did, so then there is actually a reason to put a new question. Also, the distributions and orientations are things that you could look into to see quickly, but afterwards you anyway have to quantify it. The quantitative metrics, we have been talking about them already in some lectures. We can calculate shapes or dimensions of the sample, and then with that we can establish some parameterization between parameters, input parameters, and the shapes we observe. So, one thing that is actually always happen is that we have uncertainties, and that's not new. Richard Feynman, he made this statement that scientific knowledge is a body of statements of varying degree of certainty. Some most unsure, some nearly sure, but none absolutely certain. And that actually says the thing that actually applies to imaging as well, even though it's not always so obvious how to bring it. And I'm going to show some examples now where we look. So what we want, of course, we want some error bars on our measurements, not just absolute saying the volume is this, because it's not. you have some uncertainty in your measurements. And you have to, in principle, have the mindset that each measurement has an uncertainty. And then is the question how to propagate this through the image processing process. And little bit about terminology. It's often errors are often used in a kind of a sloppy way. You say you have a measurement error, but in principle, what you're talking about, you have a measurement uncertainty, because the error requires that you have a ground truth and you can measure exactly from the ground truth to what you measured. And the uncertainty is more like a confidence interval where you say your real value is between these boundaries. So this is more the thing we are going to look into, because that one, we never have the absolute truth unless you go to the standard. So we have to work with these intervals. This PhD thesis actually tries to put even the uncertainties in the whole image processing tool chain and try to do uncertainty-aware image processing and get some nice results out of that. So, which kind of uncertainties are we actually dealing with? We have technical uncertainties on one side, where we have the metric that we have chosen, how exact is that? We have the noise, of course. We have unsharpness. Our optical system introduces some blurring. Then, depending on which image processing algorithms we are using, that can also introduce some uncertainties. And then we have numerical errors. If you do a lot of processing, you can have rounding errors here and there. If you switch between different data types, from integer data types to floating point data types, you can get some rounding errors, and that can propagate also through. But that is, in principle, I would say that is the least dominant. The most dominant ones are probably the signal-to-noise ratio and the unsharpness. To some extent, also the metric. Then we have field-specific uncertainties. So there is the question, which model are you basing your analysis on? And there can also be variations in your population, in particular if you work with biology. You never know what you know more or less what you get, but there is always a spread. Then you have also noise coming in here. So there are quite many things that can introduce uncertainties in our investigation. Then we have also two categories here. We have systematic or random contributions. So the systematic are reproducible, so they don't need a statistical analysis. We can have rounding errors, uncalibrated system that we get a bias in your measurement. Also the algorithm choice can give a bias, and so on. Then the random is the statistical fluctuations. We have random variations in the studied population, source fluctuations, detector noise, etc. that comes in to our measurement. And when we try to categorize this, we can say that we can work with precision and accuracy. And in the upper left corner, we have low accuracy and low precision. That means with the accuracy, we mean how far away we are from the actual target. And with the precision, we mean how spread the data points are. Ideally, we want to really be in the bullseye, so high precision, high accuracy, but the question is what we really can get. And that is actually what we want also to quantify, to know how well we are around. This can be translated also into statistical terms, where we instead talk about variance and bias in the measurement or the analysis. So the accuracy is then the bias, and the precision is the variance. And it's a bit so it's actually the opposite. So small variance means high precision, and a small bias means high accuracy. So they are opposite words in that sense. Then when we start doing our measurements, we have different approaches. So one is counting, and the other one is measuring. And counting, we have discrete countable items in our image. And the smallest countable item, well, what is that in our images? Yeah? Yeah. And that can then be counted in different ways. And it's also absolute values in that sense. And a basic application of counting is actually the area of a segmented region. And I'm going to show that as an example further on. Then we have the measuring. It's more related to physical quantities, and they are values that are more attached with uncertainties. And here we have again the noise and instrumentation effects. And here we can talk about mixing ratio between different from gray levels in our sample, and how to work with that. Another thing when we talk about uncertainties is that we have absolute and relative uncertainties. So on one side we can say we can measure distance with uncertainty of 1 millimeter. If you measure distance to the moon, that's fantastic. If you measure the diameter of a coin, it's maybe not so fantastic, but you don't really see it in this sense. But if you see it as a relative uncertainty, you can see that the relative uncertainty is very small for the distance to the moon, and rather large for the diameter of a coin. We're going to use both actually, depending on the analysis approach. And propagating an uncertainty is not just summing up the uncertainties, but you have to actually work through the process how the variable appeared. So if you have an uncertainty of something that is a function of x, you actually have the derivative of the function times the uncertainty that you measured, that you had as input value. And if you have two variables, then it gets a bit more messy. You have the two derivatives of the two variables, plus you have a correlation term. So if the data has, the two variables has some correlation, then you have to add this term. If they are independent, you don't need to add it. So there you have to know what kind of, if the data is correlated. Looking at an imaging experiment, we have a lot of sources of uncertainty. So we have the fuzzy overarching topic uncertainties, and they come from different things. They come from physics, they come from the levels in the images, and they also come from physical dimensions in our samples. And the physics, then we have one thing is a scattering. Is one physical effect that comes in. We have also the attenuation coefficients, and we have the effect of the optics. Then for the levels, we of course have the signal to noise ratio from the detector system, and also from the samples themselves. And we also have the gray levels. So when you acquire data, you have to quantify it to bring it into the computer. Sometimes you work with 8 bits, sometimes with 12, maybe even 16 bits. And the number of gray levels also gives you a contribution to the uncertainty. Finally, we also have dimensions. Our pixels have a finite size, and that needs to be measured. So when you do it, actually that's the first example I'm going to show, how to actually quantify the uncertainty of the pixel size. You can't trust that it is perfectly exact. So I have three examples here now. One is measuring the pixel size, one is the perimeter length of an object, and the last one is the water volume behind the pixel, which actually also introduces the gray level. So first thing is how to measure the pixel size. So to do it, if you don't know it, you have to measure it. And one thing is you need to have an object of a known size. And then you measure the same object within the image. And the pixel size is the real world object length divided by the distance of, or in pixels between two edges of that object. Then we have the uncertainty equation, how to propagate this. It looks like this, and you can see more about that in this tutorial. Then we do our measurement. We have this object. This is a special object made for neutron imaging, where we have a gadolinium sheet, which is extremely absorbing. So we have a very nice sharp edge. So I take the caliper, I measure this distance, and I measure in the image the distance between these two edges. And then we get some uncertainty. With the caliper, my caliper had an uncertainty of 0.05 millimeters. And then I measure the pixel size, doing some image processing to detect these edges, and then measure the distance between. And then I got an uncertainty of about 1/3 of a pixel on that measurement. Now, plugging that into the equation, I get finally this result. So here I just implement that equation, and the last line is just to make this text nice. So we see that we have 0.11 microns uncertainty on 43 micron pixel size. And that is something we can use later also in our calculations. Now, doing all these evaluations about error propagation or uncertainty propagation is quite tedious, and there is actually help for that. So there is an uncertainties package in Python where you can define uncertain variables, and then you do your arithmetics as you usually do, and you get the same result. So it's a pretty neat thing. It actually even has a support for NumPy, so you can do all the mathematical functions as you like. And that saves a lot of work when you want to do this. So now we just looked at one simple example. So now we want to work on the segmented images. And what we have learned to measure is area, perimeter, positions, and distances. And until now, we saw it as some kind of absolute values, no uncertainty, but how can we now propagate the pixel size among these? So let's take a look at the perimeter length. And there are a couple of things that comes into this uncertainty. So first of all, how were the edge pixels identified? There are different methods, and each method can introduce a bias. Then we have the pixel size, which we saw just now. And then later is also how was, or actually before it, how was the image segmented? Depending on where you set your threshold, you can get more or less pixels on your boundary. And unfortunately, that we have seen too, that edges are the ones that are segmented with the least confidence. So let's look at identifying the edge. There are quite many ways of doing it. In this case, we just have this edge here. So these are the edge pixels using a neighborhood of four-connected neighborhood. And let's see how we can measure the parameter of these. So we have counting pixels. That's the simple way. Then you get 18 pixels along this edge. Then a different metric would be to look at all the edges facing the background. And then you get 24 as the parameter. Another one would be to go for the center line, or actually approximation of the center line, is doing something like this, that if you have a turn like this, then you do like a half diagonal added to the size. And then you get yet another center line. There are also approaches where you can do polynomial fitting to get more exact, or spline fitting to get a more exact parameter line. But you see already here that we have a span, and depending on the choice, you also have an uncertainty in this parameter length. So let's measure it. So first step is, let's assume we got the segmentation right, just to make it a little bit easier. And we use the counting approach. And then we say that the edge is 18 pixels long. And we have the pixel size of that we measured before, 43 microns plus minus 0.1 micron. And then we can just sum up these edge pixels and get the uncertainty. This can even get more messy if you say that the pixel size is measured individually for each as a random variable. Then you have yet another calculation. But this is the simple one for the parameter. A bit more complicated is we want to measure something based on the gray levels. So in this case, I'm talking about the water volume behind each pixel. And we get from Beer-Lambert's law, we can get this D, and that is the thickness of water behind the pixel. Then the volume of water is the pixel size squared times this D. And we have now the uncertainties. We have some kind of standard deviation in the transmission, some confidence interval, and again, the pixel size. To do this calculation, it looks like this. We have, again, the uncertainty of the pixel size and the uncertainty of the thickness, and these are summed up like this. And we get our calculation. Now I did it again with the full equation and not using the uncertainties package. And then we get the volume behind each pixel with some uncertainty on it. Yeah, so these are some examples on how you can calculate the uncertainty. Another thing is, I said before that our edges, they are uncertain, but we have only qualitatively looked into that. And it's not very easy to actually quantify it. In particular, as in many cases, you don't have the ground truth. You don't know where the edge is or what the exact original was. So what we did before, we were computing computer metrics, RC curves, heat maps, etc. But all these, they require this ground truth, and now we don't have it. So what my colleague Peter Moonen did was to invent a new approach to do it. And let's assume our data is Gaussianly distributed. So we have something like this, and of course, if we compute the histogram, we can get something nice like this and do a fit of the Gaussian probability density function. And this can be used when you compute the threshold between two groups. So here we have the histograms of two classes, and we put the threshold here. We can see that there are is a great amount of false negatives and a less great amount of false positives in the data. And now we want to know how bad is it. And the approach that he introduced was, first of all, we do a segmentation, and then we try to fit the Gaussian mixture model on this data to get the Gaussian distributions of each class. We normalize these Gaussians either as peak to 1 or area under the curve to 1, doesn't really matter actually. And then we compute weights, where the weight of the observation is the same as the probability density, so the probability for class 1 or class I for that value. And as we have Gaussians, the weight comes like this. And the confidence of each class is computed as the weight for that class over the sum of all weights. And that makes it possible for us to compute the confidence of each of these values in every pixel. And here's a little example where we have two measurements. So we have the weight for class 0 is the green one, and the weight for class 1 is the red one. And then we can compute the confidence levels. We have for the class 0, we have a lower confidence than for class 1, as is natural because you hit it much lower here than here. So it actually makes sense that you have a lower confidence on class 0. Let's bring in some images. So we have 3 classes with different averages. All of them have Gaussian noise with the same standard deviation. Then we introduce some blurriness using a Gaussian filter. So this is the ground truth. These are the expected averages. So the -3, 1, and 5. Then the smoothing produces this, and then we add our noise, and we get that. And you see already that the edges, they are not so easy to determine in this. And if we compute our confidences for the different classes, so now we have 3 classes. So class 0, that is the dark one. You have in the large areas here, you have quite high confidence, but there are some places around here that could possibly be classified as class 0 also in that area. This area is so far away that it's very unlikely. Then we do the same for class 1, and you can see now that this blurry edge, it actually starts talking to us. And that is what I showed in a previous lecture, that when we have a multi-class segmentation, you often pass through the middle class. And that is what we see here, that when we go from the dark to the bright, there is also some kind of uncertainty coming in. And then in the last class, of course, we have almost nothing here because it's a large step, but there is some spillover into class 1. And our confidences now, we can look at the histograms here. You can see that the histograms are overlapping, and there is essentially no overlap between class 0 and class 2. So that's actually what we observe here. But class 1 is actually polluted by both the other 2 classes. Now looking at the confidences, we see this confidence curve comes in for each of the classes. And if we do the global confidence map as we segmented it, we can see that there is, some uncertain points within each large area, but this edge is really suffering from poor confidence. I'm not going to talk about this today, but in principle you could use this now to promote more precise, or you can do it to compute better values of parameters, etc., when you propagate this uncertainty into your different calculations. So, when does it matter? In principle, if you have a high signal-to-noise ratio, edges have the lowest confidence, and that has the impact for the parameter, tortuosity, network connectivity, and volumes of small items. That is when it starts playing a role. If you have low signal-to-noise ratio, then actually you have all the things that you had for the high SNR, but also you come into when you compute the porosity, volumes, and also even for the labeling. We saw with the watershed that you get a lot of misclassified pixels, and they introduce a lot of over-segmentation. So this brings me to the end of the first part. So we have looked at the uncertainties, and in principle, you have uncertainties everywhere. And some uncertainties can be easily quantified. The even apparatus that tells you have this uncertainty so that you can use directly. Noise can be measured. And a lot of our analysis depends even on the object pixel size ratio, how well we can determine these uncertainties, or actually determine the values themselves. And to see the effect of our processing, we actually need to run a lot of simulations to see how well it actually comes out. And that is about time for a break.